Hi, folks. Today we're going to talk about gravity waves a little bit and their relationship to black holes. So, gravity waves provide for us one of the latest and most interesting tests of relativity, um, our understanding of the fabric of space and time and how they're connected. Uh, the US over the years has built facilities called LIGO, actually two facilities. One is based in Washington State in Hanford, and it looks something like this. There's a central analysis and control station, and then two arms, one that goes out in this direction into the distance and a second arm in this direction. A second site is located in Louisiana, and it's got that same control center with one arm and another arm at right angles to each other, 90-degree angle to each other. And in 2015, when these two sites first went online, fairly quickly they detected a gravity wave that was interpreted as coming from two black holes that merged together. So here's a sort of an artist's conception of what that may have looked like. Imagine two black holes, two very dense, supermassive objects that exert a lot of gravity and bend space-time a lot, orbiting around each other, right? They're orbiting, they've got a certain period, and because the gravity is very strong, that period's very fast. Um, and because gravity will actually space-time provides a bit of a drag, a bit of friction, as these moving masses warp space-time, they produce a sort of a spiral pattern of ripples that radiate in all directions away from the spinning masses and take energy away from them. And the ripples also move outwards from the spinning black holes at the speed of light. So they're taking energy away, and as the black holes lose energy there, they orbit closer to closer, faster and faster until they actually merge. And you think that that would cause the a huge explosion, right? But because they're black holes, nothing can escape from them, not even light, and so the explosion can't escape from them. It's all tamped down, and basically the two just slip into a bigger mass black hole and nothing comes out except the gravity waves from that merger. And so, if you're close up, what happens is space-time ripples a lot. There's a large amplitude to the gravity wave as it passes by you at the speed of light. And that makes you and everything around you, all the matter, sort of pull apart and contract and pull apart and contract as that wave passes. If you're farther away, when that wave reaches you, you'll pull apart and contract less. Everything does it so nothing is damaged or pulled apart or broken in this process. It's just everything hums a little bit. If we are here on the Earth, one of these waves will pass through the entire Earth and cause the Earth and you and LIGO to vibrate back and forth real quickly. That seems amazing and astounding, but many more similar uh, chirps or signals of these waves passing have been detected since. Uh, the black hole binaries merging produce the strongest signal because they have the strongest gravity involved. A black hole orbiting with a neutron star has a little bit less gravity, so a little bit less relativistic bending of space, warping of space, and creating these gravity waves in the fabric of space-time. And two neutron stars with less mass, less gravity, less warping uh, produce a weaker signal. But all of those three types of binary objects have been detected. Um, and since these initial detections occurred, a second, or actually, I should say, a third detector, a third two-arm detector has been brought online in Italy, a fourth in Japan, and one is under construction in India. And together, they will do an even better job of monitoring and understanding what direction these gravity waves are coming from. So we can look out into space and maybe find the source of the gravity waves. Let me explain quickly here how one of these detectors looks, right, with this sort of L-shaped two-arm structure. Here it is again with the analysis center here. Um, Over here, I've got a gravity wave kind of sketched in. Imagine the solid line as a peak in the gravity wave. The dashed line is a trough, another peak, another trough, another peak. And as it moves across, the LIGO, it wiggles one arm first, wiggles the other arm a fraction of a second later. Um, and as that first arm is wiggled, it gets longer and shorter and longer and shorter, right? The actual distance between the end and the center of the device stretches as the Earth stretches. And amazingly enough, LIGO can measure the length of that stretch. It's tiny, but measurable. So we get a reading, a degree, a sense of how large the stretch was in this arm. And when the wave passes through this arm, we get a separate reading. In this particular case, our wave tweaked this arm less and this arm more. And so we would get different strength wave signals in both of those. We would measure different length changes, different changes in the length of each arm. And from the changes in the different arms, the relative strengths, we can get some idea of the direction that the wave came from. So the signal that you see of one particular wave passing through, this is an actual signal from an event. Uh, there's some sort of wiggly, noisy data over here that is sort of the general background of things moving around on Earth causing gravity shifts. But you start to see about here uh, a peak and a trough and a peak and a trough, and the amplitude, the strength of the wave is getting stronger, but at the same time, the wavelength is getting shorter, right? This is happening as the last fraction of a second as the uh, two black holes spun faster and faster, stronger and stronger, and then merged at this point. And after that, the gravity wave stops abruptly as the two black holes merge into a single larger mass black hole. That was the data that was observed for this event in Washington. Here's the data from Louisiana. It looks very similar. Here they are shown on top of each other, so you can see that they're very similar in space and time, and that confirms that it was a, a distant gravity event somewhere far away in the universe. Um, Sometimes we refer to these things as chirps because as the wavelength gets longer, we can depict the gravity wave. We can hear it. We can make sound waves that mimic that same pattern of waves. And it starts as a low frequency wave, and then it gets louder and higher. And so it's sort of a whoop, chirp sort of sound. Um, Let me show you a couple of examples of what this looks like. Here's one. Whoop. So this first one is one event. This is a different event. They sound different. They have a different, there's the background. Whoop. So those are the signals, the wave patterns translated into sound that our ears can hear of gravity waves in the arms of LIGO devices. And so together, these gravity waves allow us another test, another test of relativity in a very strong gravity, very strong wavelength, very warped space sort of environment, right? Where the gravity is so strong in a black hole that the escape velocities are getting close to the speed of light. And so we're testing relativity at extreme levels. We talked about how neutron stars allow us to test the amount of relativistic effects at moderate, and white dwarfs lesser, and in the solar system, even lesser cases, even down to the tiny amounts of relativity that we experience in our lives on Earth, practically normal Newton-like relativity levels. So this is exciting to astronomers and physicists because we're increasing the range of environments of gravities over which we can test and confirm Einstein's theories and mathematical depictions of how gravity works in terms of space-time distortions. And it further gives us confidence in the existence of things like black holes, neutron stars, and even white dwarfs. It kind of ties together that fabric of ideas and understanding in a new and important way. So I hope this is fun for you and helps you see the universe and its surprisingness in a new light. Thanks.